Welcome everyone. This video is an attempt to make an exhaustive list of all the theorems and formulas related to circle. In case we have missed one or two theorems or formulas, please make the suggestion in the comment section. Okay, full video, all the theorems and formula I have divided based on chord, your cyclic quadrilateral, tangent, tangential quadrilateral and miscellaneous categories. Now let's check the first theorem. Our first theorem, a simple one, that's the equal chords in a circle subtend equal angle at the center. So here two chords AB and CD, if they are of equal length, let's say x centimeter each, then the angle subtended by the chord AB at the center, if this angle is alpha degree, then the angle subtended by chord CD at the center will be same, that is alpha degree. And converse of this is our theorem number 2, which says that two chords here AB and CD, if they are making equal angle at the center, so they are making angle alpha degree each, then by theorem these two chords have to be of equal length. So AB length will be equal to CD length. This next theorem is also easy one. It says that equal chords are equidistant from the center. That is, the distance of these equal chords AB and CD will be equal from the center. Now distance of a line segment from a point, that's the perpendicular distance. So this perpendicular distance, if the chords are equal, then this perpendicular distance will be equal. And next theorem is converse of this, that is, if two chords they are equidistant from the center, then the length of the chords have to be equal. So if this is x centimeter, this will also be x centimeter. Let's check the next theorem. Okay, this theorem is one of those theorem which is most commonly used, that is, the perpendicular bisector of any chord will pass through the center of circle. So if we draw a perpendicular and bisector of a chord, then this line, when you extend it, it will pass through the center of circle. Let's check the next theorem. Okay, sixth theorem is similar to fifth one, but in the fifth theorem perpendicular and bisector was given and outcome was passing through the center. In sixth theorem it is from the center, if we draw a perpendicular, so center and perpendicular are given, then this line will bisect the chord, that's our outcome. Let's check the next theorem. Seventh theorem is again similar to fifth and sixth. Only thing is, in seventh theorem it's given is center and midpoint and outcome is perpendicular. So from the center, if we join the midpoint of any chord, so this chord AB is given and its midpoint, let's take it as point M. If we join the center of circle to the midpoint, then this will always be perpendicular to the chord. Let's check the next theorem. Next is we have here inscribed angle theorem, one of the most important theorem. It states that any chord in a circle, the angle it subtends at the center is always twice the angle it subtends in the remaining part of the circumference. So here the pink angle will be twice of green angle. So if green angle is alpha, then pink angle will be 2 alpha. Let's check the next theorem. So next theorem is angles in the same segment theorem. That is, if you take any chord and you draw angle on one of the segment, let's draw the angle in this major segment. Now if this angle here is alpha degree, then any angle subtended on the remaining part of the segment will always be alpha degree. Whether you subtend this angle at here in point D, this will be alpha degree, or you subtend an angle here at point E, this will also be alpha degree. Same goes for the minor segment also. If you are making angle here, then all the angles here will be equal. Not equal to alpha, but equal to each other. So if one angle is beta, then all other angles will be beta degree. Let's check the next theorem. Okay, this theorem is converse of previous theorem. It says that if a line segment is subtending equal angle at two or more points on the same side of the segment, then all those points will be concyclic. So we have a line segment AB is there, and let's assume it's subtending an angle of alpha degree at point C. Now if it subtends same angle alpha degree at point D or same angle alpha degree at point E, then all these points, that is point A and B and point C, D, E, all the points will be concyclic. Concyclic means we can draw a circle which will pass through all these 5 points. This is really interesting theorem. It states that if you take diameter of a circle, then it will always subtend an angle of 90 degree on a point on the circumference. So this AB diameter, it will make an angle of 90 degree at point C. Instead of C, if you take any point here, let's say point D you are taking, then angle subtended by this diameter at point D will be of course of 90 degree. Or you can take in this lower semicircle any point here on the circumference. So if you take point E here, angle subtended by the diameter, that will be 90 degree. Let's check the next theorem. It's converse of previous theorem. It states that any chord in a circle, if it makes an angle of 90 degree at the circumference, then this chord has to be diameter of circle, or it will pass through the center of circle. Let's check the next theorem. Okay, this theorem is most commonly used. That's intersecting chord theorem. It says that two chords, if they are intersecting at point P inside a circle, then they will cut each other such that the product of these lengths will be equal. That is, these chords are cutting each other at point P. So product of AP times of PB, that will be same as CP times of PD. This product will be same irrespective what's the original length of the chord. Where they are cutting, that also doesn't matter. If two chords intersect each other, then they will cut each other such that the product of their lengths will always be equal. And instead of chords, if we have got secants are there, that is chord AB and CD, they are not intersecting inside the circle, but they are intersecting outside the circle. Now outside the circle, if they are intersecting, we are calling them as secant. And this particular rule is still applicable even if they are intersecting outside the circle. In that case, we call them as intersecting secant theorem. And together, both the theorems together, they are called as power of point theorem. That is, PA times PB is equals to PC times PD. Let's check the next theorem. Next is perpendicular chord theorem. In a circle, same two chords are intersecting each other, but this time they are perpendicular to each other. Then using this theorem, you can easily find the radius of this circle. So if we assume the lengths here are W, X, and this is Y and this is Z, then the formula goes diameter square is W square plus X square plus Y square plus Z square. That's a simple formula where using it you can find the diameter or radius of this circle. Let's check the next theorem. Next is direct formula to find angle between two chords. Now the formula goes alpha is half of x plus y, where x is, if you take this arc AC, so x is angle subtended by this arc at the center of circle. Y is the angle subtended by the arc DB at the center of circle. And angle between these chords, this you can find even if they are not intersecting inside the circle, but they are intersecting outside the circle. So in this case, we are not calling it as angle between the chord, but angle between intersecting secants. So this angle alpha in this case it will be alpha will be half of x minus y. X is what? X is angle made by this arc AC at the center of circle, and y is angle made by arc BD at the center of circle. Let's check the next theorem. Before we move ahead, a small message. Each video needs lot of man hours and effort to make. I look forward for your support by pressing the like button and by sharing the video with others. Let's check the next theorem. This formula is really interesting. If it's given to us in a circle, the chord length is a centimeter and it subtends an angle of alpha degree at the circumference. Then we have a formula to find the radius of this circle, and the formula goes r is a upon 2 times of sine alpha. Well, this formula is actually extended version of famous sine rule. So in this sine rule, a upon sine A is b upon sine B is c upon sine C. That's we use for triangles. And this r is your circumradius for that triangle. So here this yellow triangle, if we take a upon sine A, which is a upon sine alpha, that's equals to 2r. R is your circumcircle, and using this extended sine rule, we can get the radius of this circle is a upon 2 times of sine alpha. Let's check the next theorem. Okay, this is last theorem related to chords. So given to us are two circles are there which are intersecting at point A and B, and thus AB is common chord for the two circles. And theorem states if we'll join the centers of these two circles, then it will always be perpendicular to the common chord and it will always bisect this common chord. Now next we'll discuss all the theorems and formulas related to cyclic quadrilateral. Now let's discuss all the theorems and formulas related to cyclic quadrilateral. So cyclic quadrilateral is a quadrilateral with all the four vertex lying on the circumference. And for any cyclic quadrilateral, the sum of opposite angles, that is here alpha and beta, so sum of alpha and beta will always be supplementary or 180 degree. Let's take the next theorem. Okay, this is converse of previous theorem. It states that for any quadrilateral, if sum of opposite angle is supplementary, then that quadrilateral is cyclic quadrilateral. So if in this given figure, if alpha plus beta sum of opposite angle is 180 degree, then it's a cyclic quadrilateral, meaning you can draw a circle passing through all the four vertex of quadrilateral. Let's check next theorem. Our next theorem is interesting one. It's generalization of your previous theorem where we said for cyclic quadrilateral sum of opposite angles is 180. So that we could have said sum of opposite angle is half of sum of all angles. So generalization is instead of four-sided quadrilateral, we can take any even-sided cyclic quadrilateral. Sum of alternate angles, that will be half of sum of all angles. So for hexagon, sum of all angle is 720 and half of it, that's 360. So we can say alpha plus beta plus gamma is 360 degree. Instead of 6, we could have taken 8 sides. So for 8 sides, it's a octagon is there, and sum of alternate angle will be half of sum of all angles. For octagon, sum of all angles is 6 times of 180. So that's 1080, and half of it, that's 540. So alpha plus beta plus gamma plus delta, that's 540 degrees. Let's check the next theorem. Okay, this theorem is exterior angle theorem, very easy theorem. It states that for any cyclic quadrilateral, exterior angle is equal to interior opposite angle. So for exterior angle, we can extend side length of any one side. So this side, if we'll extend it, now this angle formed here, this is your exterior angle. So this angle, if I am taking it as alpha degree, then interior opposite angle will be this angle. This angle will also be alpha degree. Let's check the next theorem. Next is Ptolemy's theorem, definitely the most important theorem related to cyclic quadrilateral. It states that for a cyclic quadrilateral with side length A, B, C and D and the length of the diagonals as P and Q, the relation between them is the product of opposite side of the side lengths is equal to product of diagonal length. That is P times of Q is equals to A times of C plus B times of D. There is one more theorem given by Ptolemy and it's called Ptolemy's secant theorem, that gives us ratio between the diagonal length if the side lengths are given. So it states P upon Q that equals to A times D plus B times C upon A times B plus C times of D. So among these two, Ptolemy's first theorem is what is used extensively in solving most of the questions. Next is Brahmagupta's formula, very important formula to find the area of cyclic quadrilateral with given sides. Formula is very similar to famous Heron's formula. So area of quadrilateral, cyclic quadrilateral is square root of s minus a times s minus b times s minus c times s minus d. You can see how similar it is to the Heron's formula. And here S is semi-perimeter. Now the next formula related to cyclic quadrilateral is if a cyclic quadrilateral is given with the sides, then you can find the radius of circle. And for that the formula is slightly lengthy, but if you will consider it's very symmetrical. Symmetrical in a sense that denominator, this is easy to remember, and numerator, this your side A is first getting multiplied with B, then with C and then with D, and the remaining sides product is getting added. So easy to remember, very rarely used, but it's a good formula if you are preparing for competitive exams. Let's check the next theorem. Okay, next is a beautiful formula related to cyclic quadrilateral whose diagonals are perpendicular to each other. That is, we are talking about ortho-diagonal cyclic quadrilateral. They have very beautiful relation between the sides, that is, sum of squares of opposite sides is equal. And amazing part is this value is also equal to diameter square. So we can use this relation to find radius of this circle. And if you are interested in area of this cyclic ortho-diagonal cyclic quadrilateral, so general simple ortho-diagonal quadrilateral area is given by half of d1 times d2. That is, any quadrilateral whose diagonals are perpendicular to each other, its area will be this. Now it can be a kite or a rhombus or a square or any quadrilateral. And on top of it, if it's a cyclic ortho-diagonal quadrilateral, then the area it's given by half of AC plus BD, that is half of sum of opposite sides. And this you can easily establish by Ptolemy's theorem. So I leave that exercise on you, so you can apply Ptolemy's theorem to get this relation here. Let's check the next theorem. Next set of theorems are based on tangent. Now tangent is a line which is touching the circle at one point. And the first basic theorem is the tangent is always perpendicular to the radius at point of tangency. So angle between the radius and tangent at point of tangency is always 90 degree. Let's check the next theorem. Alternate segment theorem. It's an important theorem. It states that angle between the chord and the tangent at the point of tangency. Now this angle will always be equal to the angle formed by the chord in the alternate segment. If you'll see, this alpha degree is formed on the minor segment. So alternate segment will be this major segment. So any angle formed in this major segment, this angle will always be equals to the angle between this chord and the tangent. That is, this angle will be alpha degree. Again, angle between the chord and the tangent, we could have taken this pink angle also. This pink angle will be equal to angle formed by the chord in the alternate segment. So this pink angle is in the major segment. So in this minor segment, anywhere in this minor segment, the angle formed will be same that of pink angle. Okay, this theorem is simplest theorem and most frequently used. That is, the tangents drawn from an external point will always be of equal length. So from point P, we have drawn two tangents PA and PB. They will be equal in length. PA equals to PB. One more outcome from it, if we'll join AB here. Now as PA and PB are equal, it's an isosceles triangle and thus equal sides have got equal angle opposite to them. So if this angle here is alpha, then this angle will also be alpha degree. Let's check next theorem. Okay, this next theorem states from an external point, when we are drawing these two tangents PA and PB, they are forming this angle at point P. And if we join this external point P to the center of circle, theorem states that this line PO will bisect angle P. That is, if this angle here is alpha degree, then this angle on the top, that will also be alpha degree. Let's check next theorem. Okay, we are at Tangent-Secant Theorem, one of the most commonly used theorem. It states that from an external point, if you are drawing a tangent and a secant to the circle, then the relation hold is tangent square, that's PT square, will be equal to PA times of PB. Let's check next theorem. Next theorem states that when two circles are touching each other, then they will have three common tangents. Those tangents are AB, CD and EF. So these tangents are common to both the circles. Now theorem states that length of these tangents will also be equal. That is, AB length will be equal to CD length. And again, these two lengths will also be equals to EF length. And the value of this length, that will depend upon the radius of this circle. And in this case, if the radius are small r and capital R, then the length of common tangent will be given by 2 times of square root of capital R times small r. Let's check next formula for common tangent. Okay, it's an important one. Now the two circles, they are not touching each other. Their centers are d centimeter apart. Now these two sets of tangent, these are called direct common tangent. And the theorem goes that these tangents will be equal in length. That is, AB will be equal to CD. And the formula for the length of the tangent, that's given by square root of d square minus difference of the radius square, that's r minus r whole square. That's the formula for length of these tangents. Now when two circles, they are not touching each other, there are total 4 tangents, 4 common tangents. The other two set of tangents, they are called transverse common tangent. Like we have got parallel line, we have got a transversal is there. Same way for this direct common tangent, we have got this transversal is there. So these are your transversal common tangent, and they will also be in equal in length. That is, this length EF will be equal to GH, and their length, they will be given by the similar formula, not same but similar formula, that is square root of d square minus, instead of difference, now here you have to take sum of the radius whole square. Let's check the next formula. Okay, this particular case, we have got 3 circles are there and they have got one common tangent. Now the relation between the radius of these 3 circles is derived from Descartes' theorem or kissing the circle theorem, which in detail is given as 50th formula in the end of this video. And a small outcome of it is what we are using to find the relation between these three radius. Now the relation is beautiful, that's 1 upon root r, that's the small circle radius. 1 upon root r is equals to 1 upon root of r1 plus 1 upon root of r2. So it's many times this question comes in competitive exams where you have to find radius of this small circle, and you can find it relatively very fast using this simple elegant formula. Okay, next is a very special outcome. So when circles, a series of circles is there which are touching each other, and the circles have got a common tangent. So there is a beautiful relation between the radius of these circles. So you can have n number of circles in this series, and the relation is the radius of these circles will be in GP, geometrical progression. That is, the ratio of the radius will be same. So any two set of circles you can take, and the ratio of the set of these circles will be same, constant. That is R1 upon R2. That will be equal to R2 upon R3. And if we have got one more circle there, then that will be equal to R3 upon R4, and so on, and this value will be constant. So if this series of circles are there and any two circle radius is given, you can find radius of all other circles using this relation. Let's check next theorem. That was all about tangent. Now let's talk about tangential quadrilateral. That's a quadrilateral in which you can draw a circle which will touch all the four sides, is called tangential quadrilateral. The first one, the basic theorem, that's Pitor's theorem. It says that the sum of opposite side in a cyclic quadrilateral will be equal. That is, w plus y equals to x plus z. Now the general form of this theorem is in case of even-sided tangential polygon, right? I'm talking about even-sided tangential polygon. The sum of alternate side will be half of perimeter, right? Here also if you will see, sum of opposite side is half of the perimeter. So the general form is, in case of even-sided tangential polygon, the sum of alternate side will be half of half of perimeter, or that will be equal to semi perimeter. That's the general form. Okay, now there is one more theorem related to this. That is, if you will join point this vertex to the center of circle, right? So if you will join A to the center, B also to the center, C to the center, and D to the center, and if you will take these angles formed around this center, then you will find that the sum of these opposite angles, that's alpha plus beta, is equals to your gamma plus delta, and is equals to 180 degrees. So that's the amazing result here. Let's check next theorem. Next is related to area of tangential quadrilateral. Now area of tangential quadrilateral can be found using very simple formula, that is S times R. R is the radius of this circle, S is semi perimeter of this tangential quadrilateral. So this formula actually is a universal formula for any tangential polygon. So if you have got a circle is there, and outside if you are drawing n-sided polygon touching the circles, then its area will be given by S times R. And this formula is at times used in reverse, where data is given related to area and the side, and you have to find the radius. So you say radius is your area divided by semi perimeter. So when I'm saying universal formula, so if you're instead of quadrilateral, you can take triangle also. So what's the radius of this circle? You'll say, sir, radius is area of triangle divided by semi perimeter. Let's check next theorem. Okay, it's an interesting one. So here what we have done is tangential quadrilateral. We have joined the vertex to the center of circle here, and full quadrilateral is divided into 4 triangles. And the amazing result here is that sum of this opposite triangle areas, that's 1 plus 3, area 1 plus area 3 is equal to area 2 plus area 4. And in fact this is valid for any even sided tangential polygon. So instead of this tangential quadrilateral, if I have a tangential hexagon, so that hexagon will get divided into 6 triangles, and area of alternate triangle will be half the area of hexagon. Same goes for octagon, decagon, dodecagon. Only condition is it has to be even sided tangential polygon. Let's check the next theorem. So here we have got a purple quadrilateral is there, and inside it we have got a circle is there. So you can call this quadrilateral as tangential quadrilateral, but the same quadrilateral is inside the brown circle. So this quadrilateral can also be called as cyclic quadrilateral. So a quadrilateral which is both tangential and cyclic, we call it bicentric quadrilateral. And area of this bicentric quadrilateral is given by amazing formula, that's area is square root of ABCD. So let's check the next formula here. Okay, this is a simple and easy one. Those who are into geometry, it's a very basic formula, that is, in case of a right angle triangle, the end radius is given by a simple formula, that is B plus C minus A. A is hypotenuse. So B plus C minus A divided by 2. It's very commonly used, and thus I have included into this list. Okay, previous formula was to find radius of incircle, that's radius for this black circle. Now what if we have to find radius of X circle? Now what is X circle? X circle is a circle touching all the 3 sides but externally. That is, if you extend this side length AC and you extend this side length AB. Now this length AB, AC and BC, if it's being touched from outside, so this circle is touching all the 3 side lengths outside, this is X circle for the triangle. And the radius for this X circle, that's given by a simple formula, that is R times S divided by S minus A, or it can also be written down as square root of S times S minus B times S minus C divided by S minus A. You can easily compare it with Heron's formula. So S minus A is not getting multiplied on top but getting divided. And how we are selecting S minus A? Because this X circle is opposite to vertex A and thus opposite to this side length A. So this S minus A is coming in denominator. So if you are making this X circle, let's say here against this AB side and outside here, then S minus C will come in denominator. So we have got one more formula here, that is your, if you draw all the 3 circles, all the 3 X circle, then the relation between the 3 X circles and the incircle, it's a beautiful relation, that is 1 by R is equals to 1 upon RA, RB, RC, which are radius of X circles. Let's check the next formula here. Okay, 47th formula, it's very important and very commonly used, that is, if a triangle is given with side length ABC, with respect to this triangle, your circle, blue circle, is circumcircle, and the radius of this circumcircle is given by a beautiful formula very commonly used, that is capital R is ABC upon 4 times of triangle area. Very important formula. And the 48th formula is also important, that is this capital R, radius of the circumcircle, is also given by A upon 2 times of sine alpha, where alpha is angle opposite to this side length A. So this angle alpha is what we are talking about. So here R can also be found by B upon 2 times of sine B, or C upon 2 times of sine C. And this formula is derived from sine rule, famous sine rule. Let's check two more theorems. Those are miscellaneous theorems. So let's see the next one. Okay, second last theorem. It's called pizza theorem. It's derived from how pizza is being cut. Okay, usually pizza is cut from the center, right? Now the theorem states that instead of center, if you are cutting it across a point anywhere on the pizza, and you are dividing it into 8, 12, 16, 20, 24 pieces, and the angle made at the center of each piece is same, right? So angle has to be same and total cuts have to be multiple of 4 starting from 8. Then the area of this orange region and green region will be equal. Now that's an amazing outcome, right? This orange region and green region, the total area will always be equal irrespective across which point you are making the cut. So instead of center, if you are making the cut on the side lengths of the diameter or anywhere on the circle, the total green and orange region will always be equal as long as number of cuts are in multiple of 4 starting from 8 and the angle of each cut is equal. Let's check last theorem, that is Descartes' circle theorem or kissing the circle theorem. It's very famous theorem, that is if three circles, black circles, they are touching each other, now you can always draw a fourth circle which is touching all the three circles. Now that fourth circle can either be this small red circle or the bigger red circle. And the relation between these three black circle and the fourth circle is what's given by Descartes' circle theorem. If we talk about this small circle, so if we take it as small r and the radius of these three circles as r1, r2 and r3, then the relation goes 1 upon small r is equals to 1 upon r1 plus 1 upon r2 plus 1 upon r3 plus 2 times of this relation here, right? And if you are interested to find the radius of this bigger circle, then formula is exactly same except for one small variation, that is instead of plus the formula will have negative sign in it and rest everything will be same. I hope you enjoyed the video. Each video involves lot of man hours and efforts to make, and I look forward for your support by pressing the like button, by subscribing and by suggesting the video to others. I will see you in next video. Till then, tata, bye bye.